Alpen Pharmaceuticals in association with Higher Secondary Principals Forum.
Students, during last class, we studied the first concept of the first lesson, relation. Now, today, we will study the second concept, and the second concept is function. Last class, we studied what is a relation, types of relations, and a different aspect with respect to relations. For today's class, we will study function, types of function, how to find the composition of two functions, and the inverse of a function. All I will explain in this class. Let us start with the definition. In fact, we will recall the definition what we studied last year. Function, the first definition here, a function is a relation from set A to set B such that every element from set A has a unique image in set B. I'll repeat, a function is a relation from set A to set B such that every element from set A has a unique image in set B. There are two keywords here. Now, what are the keywords I will underline here? Every is the first keyword here. Every is the first keyword, and the second keyword is a unique image in set B. Unique image in set B. Now, I will explain this with respect to the figure here. If I take two sets A and B, and there is a function from set A to set B. Now, according to the definition, every element from set A should have a unique image in set B. Now, every element of set A, that means you are supposed to take all the elements from set A, all the elements from set A, and if X is here and it goes to Y, then we say that image of X is Y. We say that image of X is Y, and according to the definition, because it is said here unique, image of X will be only Y. Image of X will be only Y, and we write Fx is equal to Y. So, we write f of X is equal to Y. So, I think must be clear to you now. Set A, it is necessary to take every element to form a function, otherwise it will be a relation, because definition is saying function is a relation. So, function is a relation such that every element from set A has to be taken, and each element will have a unique image in set B, and we write Fx is equal to Y. Y is called as the image, and X is called as the pre-image of Y. Now, look at this second line here. The set A is called as the domain. Set A is called as the domain of the function. So, this is the domain of the function set A. So, here what happened, unlike in relation, here the set A is necessarily a domain of the function, necessarily the domain of the function. Whereas in the relation, it is not necessary for the set A to be a domain, because what was the definition for the domain of a relation? Domain of a relation is a set of all the first elements of the ordered pair. Now, because we are taking every element of set A, here the domain is necessarily set A, The function set B is called as the codomain. So, this set is called as the codomain, and all the elements of the set B which has the pre-image in set A is called as the range. Range, a very important concept or the term range of the function. So, all the elements of set B which has pre-image in set A is called the range of the functions. See, according to the definition, it is said that every element of set A has to be taken. Every element of set A. But nowhere it is said that every element of set B has to be taken. So, supposing we take half the elements or maybe one also, if we take only this part of the set B, so this part of the set B has the pre-images in set A, okay, any y in this shaded region which I have shaded here has the pre-images, then that shaded region only is called as the range of the function. So, only the shaded region is called as the range of the function. So, this is the shaded region is called as the range of the functions. So, is it clear to you? Say a function is a relation from set A to set B such that every element from set A has a unique image in set B. So, if you see this is not a function, one to many is not a function, but one to many will be a relation. One to many cannot be a function like this, 1 going to 2 cannot be a function. Let us go to the next slide. Types of functions. There are two types here. One is 1, 1, and the other one is on 2. So, we will discuss one at a time. 1, 1 function. 1, 1 function or injective function. 1, 1 function or injective function. A function from A to B is called injective. Other name for 1, 1. So, injective is the other name for 1, 1. So, function is called as injective if f of x1 is equal to f of x2 implies x1 is equal to x2 for all x1, x2 belonging to the set A, the parent set or the domain of the set function set A. Okay. So, f of x1 is equal to f of x2 implies x1 is equal to x2. What is the meaning of this? What is the meaning of this definition? If I explain in a simple words, two different pre-images cannot have same images. Two different pre-images cannot have same images. So, what is the meaning of this? If f of x1 is equal to f of x2, that means if the images are equal, this is possible only when pre-images are equal. That means two different pre-images cannot have same images. That is the meaning of 1, 1 function. Later on the next slide, I will explain with an example which function will be 1, 1 and which function will be on 2, okay, or not 1, 1 and not on 2. And of course, I will be solving some exercises also. Now, the second definition, on 2 function or surjective function. On 2 function or surjective function. A function from set A to set B is called surjective or on 2 function if for every y belonging to the second set, that is the codomain set, there exists x in A such that f of x is equal to y. Now, what is the meaning of this? I will go back to the previous slide. I had told you here that by definition of the function, it is necessary that every element of set A has to be taken. But by definition, it is not necessary that every element of set B has to be taken. But here, if we take all the elements of the second set as well, that means every y from the codomain set has the pre-image, or in other words, the range of the function is equal to the codomain of the function. Range of the function is equal to codomain of the function. Then the function is called surjective or onto function. So, any y belonging to the codomain set has the preimage in the first set, that is called as surjective or onto function. Surjective or onto function. Let us understand these two definitions by making use of some examples. I have drawn the arrow diagram. We have taken the arrow diagram examples. Look at the first example. If I ask you, is this function 1, 1? And the answer is yes, because every element here is going to only one element this side and vice versa. So, there is a 1-to-1 correspondence between the two sets there, x1 and x2. There is a 1-to-1 correspondence between the two sets x1 and x2. And therefore, the function f1 is 1-to-1. The function f1 is 1-to-1. The first example, I am talking about the first example, function is 1-to-1. Now, let us check whether this is onto function. Look at this x2 set, which is the codomain set. E and F does not have pre-images. E and F here is two elements does not have pre-images. That is, they do not have any correspondence with, with an element of a first set, that is a domain set. And therefore, this function is not onto. The first function is not onto. Okay? Let us go to the second example which is mentioned here. Now, the question is this function 1, 1? And the answer is no, because 1 is going to be and 2 is also going to be. There are two pre-images for element B here. There are two pre-images. It is a function because every element of set A has a unique image in the set B. It is a function because f of 1 is B, f of 2 is also B, but 1 is not equal to 2. For this case, I will write here on the screen, f of 1 is equal to B, f of 2 is also equal to B, but 1 is not equal to 2. So, the reason it is not 1, 1 is mentioned here. Okay? F of 1 is B, f of 2 is B, but 1 is not equal to 2. So, this is many one function. We will not study many one in detail, but this is many one function. Is this function onto function or surjective function? And the answer is no again, because the same reason I will give as in the previous case, in the previous example, E and F does not have pre-images. E and F does not have pre-images. Let us move to the third example which is there on the board. F3 is the function from set x1 to x2. Is this function 1, 1? The answer is no. Look at this, what I am putting in the circle. Same reason as in the previous case. Okay? F of 1 is A, f of 2 is A, f of 1 is A, f of 2 is A, but 1 is not equal to 2. So, 2 going to 1. So, this is many one function. This is not 1, 1 function. Let us check whether it is onto function. Look at this set x2. Every element in the second set has the pre-image. Every element of the second set has the pre-image. A has the pre-image 1 or 2, B has the pre-image 3, and C has the pre-image 4. And therefore, F3, the function F3, the third example is 1, 1, not 1, 1, sorry, not 1, 1, but it is onto function. This function F3 is not 1, 1, but onto function. Let us check the last one, that is f4. The function number 4, the example number 4, x1 and x2 are the domain and codomain, okay, and x1 and x4, and look at this set 1, 2, 3, 4, and the other side is a, b, c, d. Now, if you look at the correspondence between these two sets, then it is 1 to 1. See, 1 is going to B and B has no other pre-image. 2 is going to C and C does not have any other pre-image. 3 is going to A and A does not have any pre-image. So, 4 is going to D and D does not have any other pre-image, and therefore, the function is 1, 1 function or injective. Okay. Now, let us check whether it is an onto function. Every element from the second set has the pre-image. There is no element from the second set, that is x4, is left vacant, and therefore, this function, the function number 4, that is f4, is 1, 1 as well as onto. It is injective as well as surjective. And if the function is injective as well as surjective, that is, if the function is 1, 1 as well as onto, then the function is called bijective function. It is called bijective function. Here, I have taken an example. Prove that the function from real set to real set given by fx is equal to 2x is 1, 1 and onto. Here is an example given. Prove that the function from real to real given by fx is equal to 2x is 1, 1 and onto. And the solution here is there on the board. What is the definition? If f of x1 is equal to f of x2, if f of x1 is equal to f of x2, and what is f of x1 by that definition? It is 2x1 and f of x2 is 2x2. So, 2x1 is equal to 2x2. You can easily cancel 2 and that will imply x1 is equal to x2. And therefore, the function will become 1, 1. fx is equal to 2x will become 1, 1 function. Now, for onto, take any y in the real set. Now, which real set? Take any y in the real set, the codomain set here. Now, what is the pre-image for any y? What is the pre-image? If you take y in the second set, that is the codomain set, real set here, what is the pre-image? And if you check properly, if f of x is equal to y, then 2x is equal to y, and therefore, x is equal to y by 2. And therefore, here the explanation is here. If f of x is equal to y, then 2x is equal to y, and therefore, x is equal to y upon 2. So, for any y, what is the pre-image we get? And the pre-image we get is y upon 2. And if we say pre-image is y upon 2, you can take any y from the real set and you can get the pre-image x as y by 2. Example, if I take 100 as y, then what will be x? X will be 50, because f of 50 is 2 times 50, which is 100. So, I have taken an example, but example cannot prove it in general, and therefore, we will say for every y in the second set, that is the codomain set, real set, there exists y upon 2, which is x. X is equal to, I wrote it on the screen here, x is equal to y upon 2. There exists x is equal to y by 2 such that f of y by 2 is equal to y. Supposing we want the answer as 1000, and therefore, x should be 1000 divided by 2, which will be 500. So, f of 500 will be twice 500, will be equal to 1000. And therefore, I can make a statement here, In real set, the codomain set, you can take any y which you have in the real set, any y, then you will get x in the first set, that is the domain set, real set, such that f of x is equal to y. And what is that x? X is equal to y divided by 2. Let us take an exercise here. Consider a function from real set to real set defined by fx is equal to 3 minus 4x. Prove that f is bijective. I will solve this problem on the board. Solution. F of x1 is equal to f of x2. Now, I am trying to prove that this function is one function or injective function. So, we will start with the definition which is already given to you. So, f of x1 is equal to f of x2. This will imply 3 minus 4x1 is equal to 3 minus 4x2. How we get this? The image of x1 is 3 minus 4x1 because we put x equal to x1 here. So, 3 minus 4x1 is equal to 3 minus 4x2. Now, this will imply minus 4x1 is equal to minus 4x2. By cancelling 3 from both the sides, cancellation law, we get minus 4x1 is equal to minus 4x2, 3 gets cancelled. This will imply x1 is equal to x2. You can cancel minus 4. So, what is the meaning of this? If images are equal, then pre-images must be equal. That means you cannot get two different images when two different pre-images are taken. And the conclusion therefore is f is injective or 1 f is injective or 1 and this is the first part because we are told to prove that is bijective. Now, what is the meaning of bijective? Function is 1 as well as onto. So, we have proved that function is injective. Now, let us try and prove function is onto. Let y belongs to the real set and this real set which I am taking here is the codomain set. Okay? So, I will write here in the bracket codomain. So, let y belongs to the real set codomain such that f of x be equal to y. Because I do not know whether y has the pre-image or not. So, I have just picked up any y from the second set, that is the codomain set, such that f of x is equal to y. So, I am assuming that there is a x such that f of x is equal to y. I am assuming, and that is why I wrote f of x is equal to y. But what is f of x? F of x is 3 minus 4x is equal to y. This will imply 3 minus 4x is equal to y. From this step, this is the conclusion. So, 3 minus 4x, what is f of x? 3 minus 4x. So, 3 minus 4x is equal to y. This will imply minus 4x is equal to y minus 3. This will imply x equal to 3 minus y divided by 4. You get x is equal to 3 minus y divided by 4. From this step, we will get this step. So, that means for any y belonging to the codomain real set here, we have x is equal to 3 minus y equal to 4. Now, what is the meaning of this? I will take an example on the right side of the board. Supposing I take y is equal to say 100. That means I need 100 as the image. So, I am looking out for what is this x. I am taking this as an example. We have already got a value of x, 3 minus y upon 4. So, supposing we take y is equal to 100 here, and therefore, according to that answer, we get 3 minus 100 divided by 4. So, x is minus 97 by 4. So, here we are getting answer saying that f of minus 97 by 4 is 100. Let us verify whether really we get f of minus 97 by 4 is equal to 100 or not. So, f of minus 97 by 4, if you look at this function, this will become 3 minus 4 times minus 97 by 4, and 4 will get cancelled. So, this is 3 plus 97, this is equal to 100. So, we have verified here for an example, if y is 100, f of minus 97 by 4 is 100. That means 100 has the pre-image. And what is the pre-image? X is equal to minus 97 by 4. This way I can take any number y here, any number y which belongs to the codomain set here, I already mentioned here, any number y belongs to the codomain set, then I can easily get x here. Because what is the denominator of this relation which we got, final relation? Denominator is 4, never ever 0, 4 is not 0, and there is no square root here. If there is a square root, you are likely to get a complex number. So, there is no question of getting any non-real number from this expression of x, which is 3 minus y upon 4. So, that means any y will have pre-image x in the domain set. So, every y here will have pre-image here, because I have taken an example here. You can take any y, I took 100 as an example, you can take any y, fraction, rational number, irrational number, any number, negative number, you will get x by using this formula, and therefore I can make a statement, therefore f is surjective. And because it is already injective here and it is surjective here, the function is bijective, injective as well as surjective, and therefore the function is bijective. We will study now how we will find composition of a function, composite function, and how to make how to find the inverse of a function, invertible function. First, we will find out what is composite function or composition of the function. Here the definition is here, okay. The function f is from a to b and function g is from b to c. These are any two functions. Then the composition of f and g is denoted by g composite f. There is a notation here, g composite f, okay. G small circle f or g composite f is defined as a function from a to c. It is a direct function from a to c. Instead of going from a to b and b to c, g composite is a direct function from set a to set c, such that g composite f of x we say is g of fx for all x belonging to a. So, g composite f of x is equal to g of fx for all x belonging to a. Now, we can find g composite f as well as f composite g for some function if it is defined properly. That we will see later when we will solve exercises. Then there is a concept called as the inverse of a function. A function f from x to y is called invertible function, if there exists another function g, from y to x such that g composite f and f composite g are both equal to an identity function. Now, what is identity function? You must have studied in 11th standard what is identity function. Identity function is a function fx equal to x. So, we may not use the notation f there, and therefore, we normally use the notation I. So, I of x is equal to x is the identity function. So, when image of any number is the same number, image of x is equal to x, we say that function is an identity function, is a straight line passing through origin, making 45 degree with the x-axis. So, identity function. So, G composite f is equal to I, f composite G is also equal to I, and then we say that G is called inverse of f, and the inverse is denoted by the notation f inverse. This is the notation for the inverse of f. So, instead of using G, we can say f inverse. And how we will write that? So, f composite f inverse will be equal to f inverse composite f will be equal to I, the identity function. F composite f inverse equal to f inverse composite f is equal to identity function. Now, look at this note. Thus, f is invertible, then f must be 1, 1 and on 2. To get a reverse function, it should satisfy the same definition which I defined for function from a to b. So, supposing from x to y, f is a function. To get a function from y to x, every element of y must be used, and it should have a unique image in the x. So, whatever definition is true for function f must be also true for function g, and therefore, we say that f is invertible, then f must be 1, 1 and on 2, and conversely, if f is 1 and 1 and on 2, then f must be invertible. So, in other words, the function has an inverse if and only if the function is bijective. The function must be 1, 1 and on 2. So, that is the meaning of invertible function. How to find this inverse and what is the procedure? I will take some exercises. Let us solve this problem. F of x is 8x cube, g of x is x raised to 1 by 3, and the question is find f composite g and g composite f. Let us first find f composite g. So, f composite g of x is equal to f of g of x, f of g of x. By definition, f composite g of x is equal to f of g of x. Now, what is gx? So, gx is nothing but x raised to 1 by 3, x raised to 1 by 3. Now, we have to find the f image of x raised to 1 by 3. So, supposing you have f of x is equal to 8x cube here, f of y will be 8y cube, f of z will be 8z cube, f of star will be 8 star cube. And now, what is our star here? X raised to 1 by 3, and therefore, this will be 8 in place of x here. In place of x, we have to put x raised to 1 by 3, the whole raised to 3. 8 y cube. What is our y here? X raised to 1 by 3. And if you simplify this, this is 8x. So, f composite g of x is equal to 8 of x, 8x. Now, let us find the other side of it. G composite f of x is equal to g of fx, g of fx. Opposite g composite f. This was f composite g. Let us find g composite f with these functions fx and gx given here. So, this is g of fx. Fx is equal to 8x cube. G of fx. So, fx is equal to 8x cube. Now, g image of any x is x raised to 1 by 3. So, g of y will be y raised to 1 by 3. G of z will be z raised to 1 by 3. G of star will be star raised to 1 by 3. And therefore, g of 8x cube will be 8x cube raised to 1 by 3. g of y, this is our y, okay, this is our y. So, g of y will be y raised to 1 by 3, and therefore, if you simplify this, 8 raised to 1 by 3 is 2, x raised to 3 raised to 1 by 3 is x. So, g composite f of x is equal to 2x, f composite g of x was 8x. Not necessarily they should be equal, not necessary that they should be equal. These functions may not be equal. Let us take one more example on the other side of the board. Another example we will take. Supposing I take fx is equal to x square and g of x is equal to x minus 2. So, these are the two functions. Fx is equal to x square, g of x is equal to x minus 2. So, let us find f composite g of x, which is equal to f of g of x, which is equal to f of x minus 2. G of x is x minus 2. Now, we have to find the f image of x minus 2. Now, what is f of x? F of x is x square, the square of whatever pre-image you have here, and therefore, this will be x minus 2 the whole square. If you simplify this, expand, this will be x square minus 4x plus 4. So, f of g of x is either x minus 2 the whole square, or in the expanded form will be x square minus 4x plus 4. Now, g composite f of x, g composite f of x is equal to g of fx is equal to g of fx, and therefore, this is g of what is fx? X square. G of fx. Now, fx is x square. Now, we have to find g image of x square. Now, g image of x is x minus 2, and therefore, g of x square, okay, you can try by yourself as well. G of x square will be x square minus 2, because x square is x for g image, okay. So, g image of x square will be x square minus 2. So, here f composite g of x is x minus 2 the whole square, and g composite f of x is x square minus 2. As earlier I have said, not necessary that they must be equal. Let us solve one problem. How to find the inverse? Consider a function from real set to real set defined by f of x is equal to 4x plus 3, a very simple problem. Show that f is invertible and find inverse of f. Now, there are two parts for this question. The first part says that show that f is invertible. And the second part is find the inverse of f. So, there are two parts here. Show that f is invertible, find the inverse of f. Let us solve the first part. Now, clearly I told you function is invertible if the function is 1 1 and on 2, that is function must be bijective. So, first we will show that the function given here is bijective. So, f of x1 is equal to f of x2. I am proving here that the function is 1 1. So, f of x1 is equal to f of x2 implies 4x1 plus 3 is equal to 4x2 plus 3. Cancelling 3 both the sides, you get 4x1 is equal to 4x2. Implies that x1 is equal to x2. The meaning of this is you cannot get the same images unless the images, pre-images are different. So, here if images are same, then pre-images are also same, and therefore, f is 1 1. Injective or 1 1. So, in the bracket I will write injective here. Now, let us prove that this function which is given here, because we have to show that this is invertible. So, 1 1 and on 2. So, we will prove that the function is also onto. So let y belongs to the real set, the codomain set, this real set, the codomain set, such that fx is equal to y. I don't know whether the pre-image exists or not. We are just writing f of x is equal to y. Now, what is this implying? This implies that 4x plus 3 is equal to y. This will imply x is equal to y minus 3 divided by. And you remember when I took one exercise earlier, I had proved that a function is 1, 1 and on to a similar problem was taken, and for any y belonging to the real set, the codomain set here, there exists x such that f of x is equal to y, such that f of x is equal to y, and therefore f is onto surjective. Therefore, f is onto surjective. So here we have proved the function is 1, 1, and we have proved that the function is onto. If the function is 1, 1 as well as onto, then therefore the function is bijective. F is bijective, both 1, 1 as well as onto. And what is the statement we made earlier? We made a statement for inverse. If the function is 1, 1 as well as onto, that is function is bijective, then there exists a function g such that f composite g and g composite f will be equal to identity function. So what is that g? So this is what we get x. When I write y is equal to 4x plus 3, here y is defined in terms of x. Y is in terms of x. X is independent, y is dependent. Whereas here we got x is equal to y minus 3 divided by 4. So x is defined in terms of y. So y is independent, x is dependent here. X is defined in terms of y. So we get a reverse answer here. This x is giving you reverse answer. We take y from the second set and we get x from the first set. That is a domain set. This is the domain and this is the codomain. So we will define, let gx be equal to, I define a new function from real to real, of course, from real to real, reverse, okay, from real to real. This is real set, this is also real set. So g we will define from this real set to this real set. So g of x is equal to x minus 3 divided by 4. Exactly what we get here, we define gx equal to x minus 3 upon 4. Now let us see whether this g which we have defined is an inverse function of the function f or not an inverse function. Because we already said that the function has inverse. How we know that the function has inverse? Show that f is invertible. This part is already done. F is bijective. So bijective means there exists a function g such that f composite g and g composite f is equal to I. So this is gx here, gx equal to x minus 3 divided by 4. So let us find f composite g of x, and f composite g of x is f of g of x, and therefore this is f of x minus 3 divided by 4. Because g of x we have defined as x minus 3 divided by 4. This function y minus 3, we can take any notation. So this is x minus 3 divided by 4. Now f image of x minus 3 divided by 4, what is f of x? F of x is 4x plus 3 here. So this is x for f image. So 4 times x minus 3 divided by 4 plus 3. by the definition 4x plus 3. This is 4x plus 3. And therefore, by cancelling 4, we get x minus 3 plus 3, which is equal to x. Now, we started with x, students. We started with x and we ended with x. And earlier I told you this function, when we start with x, we end with x, that function is called identity function, I. So, we got f composite g is equal to I. Now, we will prove the other way around also is true, okay, and we will find g composite f. We will find g composite f. I will do it on the right side of the board here, g composite f of x. Because we found here f composite g of x, we got identity function. So, g composite f of x is g of fx and g of fx. Now, what is fx? Fx is 4x plus 3. So, 4x plus 3. And we define g of x. I wiped out from the board, but I will write here g of x is x minus 3 divided by 4. This is g of x. G of x is x minus 3 divided by 4. So, g image of 4x plus 3, this is x for g image. So, what is g of x? X minus 3 divided by 4. So, this image will be 4x plus 3, this is x minus 3 divided by 4. You cancel 3 and after that you can cancel 4, you get x. So, g composite of fx is x. So, we started with x, we ended with x. This is nothing but identity function, and therefore, we get g composite f is equal to I. So, we got here f composite g is equal to I, we got here g composite f is equal to I, and therefore, we write f composite g is equal to g composite f is equal to I. Now, what is this? This is nothing but definition of the inverse which I gave you earlier. F composite g is equal to g composite f is equal to I. That means there exists a function g such that f composition g, g composite f is equal to I, and therefore, we write final step here, E inverse of x is nothing but g of x. And what is g of x? We define f inverse of x is nothing but x minus 3 divided by 4. So, reverse function, the inverse function, okay, of the function fx 4x plus 3 is x minus 3 divided by 4. So, what did we study? Can I recall? If I recall everything what we studied for today's class, we started with the function, types of function, 1 1 on 2, that is injective and surjective, and if the function is both 1 1 and on 2, I told you it is called as a bijective function. After that, I told you how we find the composition of two functions, how we combine two functions, function inside a function, that is called as f composite g of x and f of g of x. And the last concept we learned from today's class is very important concept called as a inverse of a function. Inverse of a function, how we define the inverse of the function. Inverse of the function f exists if the function is both 1 1 as well as on 2 when it is bijective. And I have solved a problem here to explain to you how you find the inverse of the function, and it is clearly mentioned here how you find the inverse. So, inverse exists because there are two parts here, show that f is invertible. That is why we proved that the function is bijective, the first part, and the second part we found the inverse, and that is g of x is equal to x minus 3 upon 4.
Prudent Scholars, powered by Lupin Pharmaceuticals.